Hello, everyone. I am gonna talk about my last accepted paper in EUSIPCO 2022, which is entitled as User Localization Using RF Sensing, a performance comparison between LIS and millimeter wave radars. So basically, the first or the main goal of this paper is to compare both technologies, LIS and millimeter wave radars, in a localization task. So for that, what we do is we develop an experimental setup with the millimeter wave radar, and as in LIS, still the design is not feasible in real world. We would perform a comprehensive set of simulation that mimic the experimental setup in order to compare these both technologies. So basically, here we can see the setup. First, what we do is we deploy an LIS in the top of the ceiling. So we can see here, an LIS is mainly a surface composed by many antenna elements closely spaced. And here we have what we call some random active devices. So these random active devices are actually, we can think of them like smartphones, laptops, or any wireless device that is using wireless signal for their purposes. So we basically piggyback these signals to perform the sensing. And then in the radar experimental setup, what we do is we deploy a radar, a millimeter wave radar on top of the ceiling. And we try also to perform the sensing tasks, which is gonna be localized in the target user. So here in the middle of the poster, we can see an explanation of the both system models. So first, in the left-hand side, we have the system model of the millimeter wave radar. So basically we send a signal, measure the reflection, and we have a two-step process. So first, the radar processing pipeline, and secondly, the point cloud processing pipeline. So basically we receive the signal, we apply a range FFT, a Doppler FFT, the SFAR algorithm, and an angle FFT, 3D, basically to get the point cloud. So the point cloud basically is a kind of a 3D representation of the environment. And then with this point cloud, we will rely on some machine learning algorithms in order to infer the localization on the user, and at the end, the bounding box prediction. So basically our goal is gonna be predicting a bounding box around the user and predicting the localization of the target. So then if we take a look at the second part, the LIS system model, we have, as I said, some random active devices, some random smartphones, some random laptops, random routers, whatever. And then what we do is we measure the reflected signals on the target and the LIS. And then we have also, again, a two-step process, the signal processing pipeline and the radio map processing. So in the signal processing pipeline, what we do is we measure the received complex signal at the LIS viewpoint. And then, of course, as you are in an indoor propagation condition, we have to assume a spherical wave propagation. So basically for that, we design a spherical wave match filtering that I will be discussing later on. Mainly with this spherical wave match filtering, we can obtain what we call a radio map. This radio map kind of represents the environment. And this radio map, the user, the target, is gonna act as a virtual source. And this virtual source is gonna be detected in the radio map by just doing a peak localization in the radio map. So in this way, we will be able to compute the bounding box and infer the localization of the target. So then we have the LIS radio map generation. So basically, again, due to the LIS dimensions and proximity in the setting, we are under the near field condition. So this means that we need to assume a spherical wave propagation. So this leads to an steering vector on the surface that is proportional to this expression, the following expression. We can see that it differs from the far field steering vector notation. And then mainly with that, what we are going to compute is a spatial match filtering around the entire surface, such that we can obtain a radio map of the environment. So in this radio map, the passive participant will act as a virtual source and will be captured by the map. Here, this is something that we can see here. Here we have an exemplary radio map. Of course, this is a proof of concept. So we have an empty room. There is no scatters right now besides the walls and of course the ground. But basically we can see that in this empty room, we have the user is localized around here because there is a region which is more dominated or with a higher value at the output of the match filter. So we can infer that the passive target is around this area. So mainly, again, the goal of this paper is to compare these both technologies, and in the experimental setup, what we did is actually the same. So we deploy the same setup, and then we measure the performance. So here we can see a comparison of this performance. We leverage the performance by two metrics, mainly the intersection over union and the distance error. The intersection over union is basically a metric that show us the degree of overlap between the bounding box prediction and the ground truth bounding box. So here we can see first the left part of the figure, the actual score of with both technologies, the LIS and the radar. We can see that the radar and the LIS have a similar score. Of course, if we take a look into the distance error, we can see that the radar outperforms LIS. We want to highlight, or I want to highlight, that this is something we expected at the first, when we started the experiment. We knew that the millimeter wave radar, or we assumed the millimeter wave radar was going to perform better than the LIS in terms of sensing and localization, because it's a device that is actually designed and deployed for that. So it makes sense that it's going to be more accurate. But here, the point that we want to raise is that LIS is one of the breakthroughs of the massive MIMO technology, and its communication capabilities are being understudied, and they are being shown to be like a promise of the next generation of massive MIMO. So basically, we can see, or we can say, that the LIS is really attractive for communication tasks. But what we wanted to show here that also LIS is useful for sensing tasks. This is really nice because we can see that we have a close gap in performance between a dedicated device for sensing and a device that is mainly for communication. So basically, this means that with LIS, we would be able to get a system that that provides both sensing and communications in the same device. Also, it opens a wide variety of combinations. Of course, we can use radar for sensing to help or aid the LIS in the communication task. But here, mainly the point is that the LIS is sufficiently enough accurate to perform both tasks in just one device. Of course, again, this is really interesting because if we think, for example, of a beamforming scenario, it's true that maybe having a 7 centimeters different error in an analog beamforming doesn't really impact too much in the performance. So again, this defends or supports the idea that LIS should be more than sufficient for integrating both functionalities, sensing and communication. Yeah, so this is the end of my presentation. If you have any questions or anything, please drop me an email, and see you.